Hi everyone, welcome to the lecture series on computer architecture and organization. This is topic 2 and the unit 2, that is computer arithmetic. In this we are going to see about this multiplication both for signed and unsigned integers. So this is about multiplication. So multiplication is vexation, whereas division is as-bad. The rule of 3 doth puzzle me, and practice drives me mad. So this is from Elizabethan manuscript 1570, and this is written. This is an anonymous quote. So whatever the operations we are practicing in arithmetic, only practice makes a man perfect. So practice drives me mad. So this is a very interesting word, that is drives me mad. So if you practice altogether all the operations, if you practice anything that is very difficult to follow, then at last it becomes mad. Once you understood, it becomes mad. So so what is this is that multiplication and division is a very complex process, and if we practice again and again, it will be very easy for us and will be very interesting. So we know we know about this operation, and the first is multiplicand, and by what we are multiplying is the multiplier. Okay, so here multiplicand is 1 0 0 0 and multiplier is 1 0 0 1. So this is a normal multiplication. First we should multiply this with 1. So if you multiply with 1, then multiplicand will be as it is the result. So 1 triple 0. And again if you multiply it with 0, then all the terms become 0, and we need to shift one position. So if we shift one position, then it will become 0 0 0 and 0. So now again we need to multiply with the third bit, that is 0. So again the result will become 0. So 0 intermediate, these are all intermediate results. So intermediate results will be 0 0 0 and 0. And again last bit, that is the most significant bit of the multiplier, is that gives the result of 1 triple 0. So shifting, and we are placing the result, intermediate result 0 0 0 1, and altogether we are adding this 0, and 0 plus 0 is 0, and 0 plus 0 plus 0, which is equal to 0, 1 plus 0 plus 0 plus 0, which is equal to 1, 0 plus 0 plus 0, which is equal to 0, 0 plus 0, which is equal to 0, and 1. Okay. And in this multiplication, in the previous example, we restricted the decimal digits to 0 and 1. So with only two choices, each step of the multiplication is very simple. So we are gifted with only zeros and ones. If you go for the decimal digits, it takes from 0 to 9. So it takes so many numbers. So it will be very complicated. But here we are gifted with only zeros and ones. If you multiply with 1, the multiplicand will be the result, the intermediate result as it is. If you multiply with 0, then the intermediate result will be 0. So that is only, we are gifted with only two options. So it is easy to perform the multiplication operation, but we need to frame an algorithm so that the hardware architecture can execute this operation and it can store the product in the memory. So the first step is that just place a copy of the multiplicand, that is 1 into multiplicand, in the proper place if the multiplier digit is a 1. If it is 1, what we need to do, we need to multiply this 1 bit, the bit 1 with the multiplicand. We need to just place a copy. Just we are copying the multiplicand and placing in the intermediate result. If it is 0, then if the digit is 0, we need to place 0 in the proper place. That's it. So this is the first version of the multiplication hardware. So it includes this multiplicand, that is multiplicand register, and this is multiplier, by which number we are multiplying the multiplicand, and ALU, that is the arithmetic and logic unit. So that performs the multiplication operation. and this is the product register or end register in which we are storing the result, and this is a control test. So control test, in the sense, we saw about the two options, one is 1 and another one is 0. If it is 1, then what we should do, we should shift the multiplicand, we should add the product with it. That is an algorithm. It is an algorithm, so it goes according to that. If it is 1, then we should add the multiplicand with the product, and we have to place the result again in the product register. So likewise the control goes, if it is 1, it has to perform one operation. If it is 0, it has to perform another operation. That is the duty of this control set. So this is a multiplication algorithm. So algorithm is nothing but the words used by programmer when they do not want to explain what they did. So if you go through the algorithm, it clearly explains what the operation does or what the process does. So here, coming to the point, we have to start the operation, then we have to test the multiplier. This is our first step. If it is 1, the multiplier, the bit is 1, then what we need to do? We need to add the multiplicand to product and place the result in the product register. And if it is 0, then we need not to do this operation. We can directly come to this step. Step number 2. Okay. So if it is 1, what we need to do? We need to add the multiplicand to the product and we have to place the result in the product register. If it is 0, then directly we can come to step 2. So what is step 2? Shift the multiplicand register left 1 bit. We need to shift the multiplicand register to left, that is by 1 bit. And the step 3 is shift the multiplier register right by 1 bit. So we need to shift the multiplier right, and before that we need to shift the multiplicand left. Okay, and we need to come to this decision. So decision box, this speaks about this will check whether this is the 30-second repetition or not. So if it is not the 30-second repetition, then it forms a loop. So again it goes back and perform. Why we need to go for this 30-second repetition? Because it is in 32-bit register, so we are performing for 32-bit. So if it is 30-second repetition, then it will come to the end of that operation and it will store the result in the product register. If it is not, then again it goes back to the start of the operation and it performs all the sequence again and come to the point. Okay, so this is a loop. So this is a refined version of the multiplication hardware. So what is this is that the product register, it is of 64 bits. Okay, so if you compare with the previous version, the multiplier, separate multiplier register which we have here is gone. So separate multiplier register also disappeared and the multiplier is placed instead in the right half of the product register. So multiplier is placed here. Instead of keeping it outside, it is being placed inside. So control test gives what we should, at what time we need to shift, at what time we need to add, at what time we need to write the result into the product register. So that is taken care by this control test. So this is a multiplier. Now we are going to perform the multiplier algorithm. So use 4-bit number to save space. Multiply. So we are in order to save the space, we are using only the 4-bit number. Okay, instead of 32-bit, we are performing the operation on only 4-bit. So the process continues up to the 4th repetition. Okay, the iteration will go for only 4 times. So multiply 2 into 3 or 2 for 2, the binary notation is 0010 and for 3 it is 0011. Okay. So this is our iteration and the step multiplier, multiplicand and product. In this table we are going to perform this multiplication operation. Okay. So this is a register in which we are going to perform this multiplication algorithm. Okay. So what is the first step? First step, this is 0. The iteration number is 0. And the initial values are 0011, which is in the multiplier, and multiplicand it is 0010, and since we need to save the extra bit in case we can't expect the product to be exactly 4, so we must extend it to another 4 bits. So it is of 8-bit register, that is 0010 and 0000, and this is a product one. Initially the product will be, initially the register will be at 0. So it is 4 zeros and 4 zeros, totally 8 zeros in a register. So what is the first step? The first step is that we need to check the multiplier, whether it is 1 or not. Okay. So first we need to check this bit. So the multiplier which is here is 1. So what we must do is that we must perform the 1A step. So what is 1A in the algorithm? So this is our algorithm. What is 1A? Add multiplicand to product and place the result in product register. So so we are going to add the product with the multiplicand and we need to place this in this product register. Okay. So now the multiplier will be as it is. Okay. So what is the multiplier register? It is 0011. Now I want to add this multiplicand with the product. I want to add this multiplicand with the product and I need to keep this in product register. Okay. So 0000. If I add these terms, then it becomes 0010. Okay. Now the multiplicand will be the same here in this step. What is the second step? So second step is that we need to shift left multiplicand. So we need to shift that multiplicand to left, that is by 1 bit. Okay. So that is the algorithm. Shift the multiplicand register left 1 bit. So now I want to shift to 1 bit. So if I want to shift left in the sense this 1 comes to this position. Okay. So now it is 0000 and again 0100. Okay. And this will be as it is, that is 0011, this multiplier, and the product register will be as it is 0000 0010. And here the third step, we need to shift the multiplier left. Okay. So shift this is right. Okay. So this is shift right. Okay. So shift right multiplier, I need to shift to the right to one position. So I need to give a push from this side. So now it becomes 0001. So this 1 becomes here and this 1 has gone. Okay. Now what is the multiplicand? It is 0000 and 0100. Okay. And now what is the product register? It is 0000 0010. And the next thing, this is our second iteration. So the control will come here and check whether this is the fourth repetition or not. So if it is not the fourth repetition, then it's again go back to the loop. So first step, again we need to go for the check for the multiplier. So what is the multiplier in this bit? It is 1 again. So what we need to do, we need to add the multiplicand with the product and we need to place that in the product register. Okay. So in the product register, we need to add these two. So multiplicand and the product register. So what is the end result of this? It is 0000 0110. Okay. Now the multiplicand will be as it is. That is 0000 00 and the multiplier will be as it is 0001. Now I want to shift left the multiplicand. I want to shift this multiplicand. So it comes to 000 again 0 and 1000. Now the product will be 0000 multiplier will be 001. Now I want to shift right the multiplier. So if I give a push from this side, then this 1 goes out of this 4-bit register. So it comes to 0000. And what is this? Multiplicand is 0000 1000 and the product will be 0000 and 0110. And it will check for the iteration whether it is the fourth iteration or not. If not, again it goes back to the loop. So what is this third iteration? Coming to the third iteration, now the multiplier is 0 here. Okay, if you observe, multiply is 0. So 0 in the sense there will not be any operation. We need to write as it is. So 0, 0, 0, and again it comes to 0, 0, 0, 1, 0, 0, and 0, 0, 0, 0, 0, 1, 0. And now it is shift left multiplicand. So I want to shift this multiplicand to left position. So it comes to 0, 0, 0, and it becomes 1 here, 0, 0, 0, 0. Okay, and this will be the same 0, 0, 0, 0, 1, 1, 0, and 0, 0, 0, 0. And now I want to shift the multiplier to right. So shifting 0, it doesn't make any sense. Anyhow, it does the performance because it is the third iteration. So now it comes to 0, 0, 1, 0, 0, 0, and 0, 0, 0, 0, 0, 1, 0. So now again it checks for the iteration whether it is 4. If not, it checks the multiplier. So what is the multiplier here? It is 0. So if it is 0, then again we need to, there is no operation. So 0, 0, 0, and 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, 0. So now I want to shift the multiplicand to the left. So this remains the same 0, 0, 0, 0, and I want to shift this multiplicand. Now, so now it comes to 0, 0, 1, 0, 0, 0, 0, 0. The product will be the same 0, 0, 0, 0, 1, 1, 0. So I want to shift the multiplier to the right. So 0, 0, 0, and here it is 0, 0, 1, 0, and 0, 0, 0, 0. And now the product will be 0. So what is 2 into 3? It is the 2 into 3 is, it is 6. Okay, 6 to the base 10. So now we have got the result as 0 and 6. So what is the binary for 6? It is 0, 1, 1, 0. So the end result is 0, 1, 1, 0. Okay. So this is the algorithm. So what we have done is that first we need to initialize the registers with the real values. So multiplier here it is 3, so 0, 0, 1, 1, and multiplicand is it is 0, 0, 2, so 0, 0, 0, and 0, 0, 1, 0. Product register will be initialized to 0, and we need to check the multiplier at the least significant bit. So multiplier is 1. If it is 1, then we need to perform the operation 1a, which is product is equal to product plus multiplicand. So we have added this multiplicand and product, and we have placed the intermediate result in this product register. So if then what is the next step? We need to shift the multiplicand to left, and the next step is we need to shift the multiplier to right. So this is 3 steps. So if not, if it is not 1, then there will not be any operation, and the 2 and the step 2 and 3 remains the same. So this is a very simple algorithm. This is a very old algorithm, traditional algorithm, which is being followed for many years, and this is the basic of this multiplication architecture. Okay. So if we want to unroll the loop, what we need to do is that we need to do everything in parallel. So what is the unrolling the loop in the sense? If you observe here, rather than using the single 32-bit adder 31 times, this hardware unroll the loops to use 31 adders and then organizes the delay. Okay, so all the adders will be working at a time, and then it organizes the delay. Okay, so this is about the overall summary of this multiplication. Multiplication hardware simply shifts and adds as derived from the paper and pencil method learned in grammar school. Compilers even use shift instructions for multiplication by powers of 2. With much more harder, we can do the adds in parallel and do them much faster. So we can multiply in MIPS. If we want to do this multiplication in MIPS, then it uses a pair of registers in order to store the 64-bit product. They are nothing but this high and low register. Okay, so high and low register. So to produce a properly signed or unsigned product, MIP has two instructions. One is multiply, which is represented by MULT. Okay, so mult. And if it is for unsigned, a U is added in this instruction, that is multu. So to fetch the integer 32-bit product, the multiply uses move from low. Actually, we need to fetch the product. Okay, it is a 64-bit product register, but we need to fetch the 32-bit product. So what the programmer uses, the instruction used by the programmer is move from low. So it is MFLO. Okay, so it fetches only the 32-bit product. The MIPS assembler generates a pseudo instruction for multiply that specify three purpose registers generating MF low and MF high instructions to place the product into registers. Okay, and this is by the latest version, by the last architecture we have seen. So this is the latest and the fast multiplication hardware. So this follows the pipelining architecture, hence pipelining symbol has mentioned here. In the unit 1, we have learned the great ideas in computer architecture, and one of the 8 great ideas in computer architecture is pipelining. It is nothing but a pattern of parallel operation that is followed by the processes. Okay, so that's all about this multiplication algorithm. Thank you for watching. Continue watching.